Let's talk about differentials. In the equation dy dx equal to f prime of x, we can regard the dy and the dx as something we call differentials. And when you think of a differential, you really want to think of dy as a very small change in y and dx as a very small change in x. The equation dy is equal to f prime of x times dx. This is known as the differential form of the equation dy dx equal to f, oops, there's a prime missing there, prime of x. Okay, so let's look at a couple of examples. In example 4, we're asked to find dy and evaluate it when x is equal to 3 and dx is equal to 0.1. So the first thing we'll do is we'll calculate the derivative dy dx, and I use the power rule for the x squared to get 2x, and then I use the constant multiple rule to get plus 2. Now, I'm going to regard dy and dx as the quotient of two differentials. So in order to find dy, I'm simply going to multiply both sides by dx, and I get dy is equal to 2x plus 2 dx. And just so it's clear, I'll put parentheses around the 2x plus 2, so you don't accidentally only attach the dx to 2 there. So now I can substitute in the x value of 3 and the dx value of 0.1, and I'm going to get 2 times 3 plus 2 times 0.1. And when I plug that into my calculator, I get 0.8. So this is the small change in y that I was referring to. Let's highlight that. Okay, let's take a look at example B together. I'm going to take the derivative of both sides, so I get dy dx is equal to negative sine of x. I multiply both sides by dx because I'm treating the dy dx as a quotient of differentials, and I get dy is equal to negative sine of x times dx. And when I plug in my point this time, this is going to give me negative sine of 3 times 0.1. Plugging that into my calculator and rounding to 3 decimal places, I'm going to get 0.0141. So I'm going to highlight that answer as well. So in case it wasn't clear, I probably should have written this earlier. Just want to emphasize is a small change in y, and dx is a small change in x. All right, cool. Let's try to connect differentials to linear approximations. Now, differentials can be used to approximate the actual change in the value of a function, f of x, resulting from a small change in the input values, x. So when I talk about the actual change in the value of the function f of x, I'm going to highlight that in red. This is what we're going to call delta y. Now, this small change in input values x, this is what we're going to also refer to as delta x. Okay, so let me set up a picture downstairs for you. Here we have our original x value a. That's the place where we're having our linear approximation anchored. And we're just going to deviate away from a by a little bit. I'm going to make it bigger so that you can sort of see more clearly in the picture what's going on. And what I'm saying is we're going to call the distance from a to x delta x. So you can imagine that we're just deviating from a by some small amount. Okay, so I'm going to draw a little triangle here. This side of the triangle is the distance from a to x, so that's the delta x part. And if I labeled on this y-axis over here, the y value over here is f of a. Great. Now, when I look at the actual function value at x is right here. So when I label that y value is f of x up here, like this. And I'm going to label this side of the triangle as so. So what I'm saying is the true change, the actual change in the value of my function is going to be what we call delta y. All right. What I want to do is I want to use differentials to approximate, use differentials to approximate delta y. And which differential am I going to use? I'm going to use the change in y values of my line. So if I were to come to my line and drop, from the line down to the original y value, this little blue line I've just drawn here, this is my differential dy. Okay, so we're really using the differential dy to approximate delta y. Now, we need a dx as well, and dx is going to be the same as delta x, like this. Okay, so what I'm trying to tell you is that when we use differentials to approximate the change, we're basically going to say this: delta y is approximately equal to dy, which is really equal to f prime of a times dx. You could also write this as f prime of a times delta x because, again, delta x and dx are the same. In fact, these guys are our independent variable. Independent variable. And the dy is our dependent variable. Okay? So I'm going to highlight this, this equation. Delta y is approximately equal to the differential, and we can calculate the differential as we did above. Let's take a look at an example. Let's look at an example 5 here. They give me a curve. So this is like the red curve I have up above, and they're saying y is equal to x squared plus 2x. We want to compute delta y, and we want to compute dy at x equal to 3 if delta x or dx is equal to 0.1. Let's calculate delta y first. So maybe I'll do this in red so it matches our picture up above there. Delta y is going to be equal to the change in the y values, right? So how do I calculate the true change in the y values? Well, the bigger y value is going to be f of 3.1 because I'm evaluating at the point x equal to 3, which kind of corresponds to my a, and then I'm going 0.1 distance more, which means my x value up here is going to be 3.1. So I'm putting my 3.1 there. And then I'm going to subtract what I get when I evaluate my function at 3. Okay, and I'm just going to plug each of those numbers into my equation. So my equation, I'm thinking of this as f of x is equal to x squared plus 2x. So plugging into my calculator, I get that f of 3.1 is 15.81, and f of 3 is 15. All right. So when I subtract these, I get 0.81. This is the true change in the y values. And that's from a small change of 0.1 in the x values. Now, when I want to calculate dy, this is the same as example 4a, right? So we actually just did this example a few moments ago, and we got that the change dy was equal to 0.8. So let's compare now. The true change in the y values when you shift the x value by just a small amount, just 0.1, the change in the y values is going to be 0.81, okay? And our approximation for that was dy. When we did our example earlier, we saw that we got 0.8. And 0.8, well, that's pretty close to 0.81. So this kind of shows that our differential is a good approximation for our true change in the y values. All right, everybody, let's talk more about this in class together later. Take care.